Okay, so let's start today's lecture. Now, any questions? Finally, somebody is answering my any questions.
I have a problem with the garage and car question. Garage and car question.
Okay.
I thought that it should be solved using space-time interval.
First, describe the problem. I don't remember the question.
There is a car approaching to a garage at 0.9.
Okay. So this is the garage. There's a car approaching.
0.6.
At the speed 0.6 c.
The moment car reaches the front of the garage,
The front is here. Which side is this side is the front. Okay, so the car is now here.
the side that your door opens, the other one closes.
Okay. So at this instant, this door is open. The other one is closed.
No.
No.
At first, this one is closed. This one is open. When it reaches, this door opens.
Okay.
And the other one closes. And in the reference frame of the garage, they are simultaneous.
They are?
Instantly simultaneous.
Okay.
My way of solution is, and it has that in the reference frame of the car, the difference between movements of the doors.
The time difference.
Yes.
Okay.
My way of solution was using space-time interval.
Which is how you solved it?
I said in the reference frame of the garage, the two doors have 5 meter separation. And they move simultaneously, so their delta T is 0.
Okay.
In the reference frame of car, I guess the delta X was 4 meter. Using length contraction, the doors was 4 meters apart.
This is 4 meters.
And the space-time interval between those two events must be equal in each reference frame.
Okay.
However, my solution is different than most of my friends. I wonder what is the correct way to.
Well, let's say I think you said that delta x squared minus c times delta t squared, which in this reference frame is just 5 meters squared. You say that this should be equal to delta x squared in this reference frame, which is 4 meters squared, minus c times delta t squared. This should be also, these two should be equal. This is what your claim is. So can they be equal? First of all, let me ask this question.
I guess they should be because they are same events.
Well, you see, the one problem that I see in this equation is the right-hand side is less than 4 meters squared. Because this is positive. So it can never be equal to 5 meters squared.
I switched
the order. But you see, this combination should be the same for everyone. You cannot just switch the order as you wish. You cannot just set this quantity equal to minus this quantity in some other reference frame. If you are defining the invariant quantity as delta x squared minus c times delta t squared, it should be the same way in every reference frame. Why doesn't this work? No, I mean, let's stick with this solution. I mean, the solution is wrong. But why? I mean, what was his mistake? Why should it be? Yeah, that's what he is looking for. He is saying that delta t is different. So delta t should be non-zero, and he's proposing to extract delta t from this equality. So what you are proposing is basically what he is trying to do. Why? What should it be? But you see, we have the garage which is at rest, and in its rest frame, its length is 5 meters. Then we go to the other reference frame, which is moving with a speed 0.6 c. In that new reference frame, the length of the garage will contract. The position of the events will be different. You see, what are the events? Always, I mean, it's a good idea to always write down your events. Event 1. Left door opens. Well, let's say it is at x is equal to 0, t is equal to 0. This is my event. X is equal to 0, t is equal to 0, of course, in this reference frame. And then event 2. Right door closes. Well, this happens at x is equal to 5 meters, and still t is equal to 0. These are my two events. So if you calculate this quantity, you will get 25 meters squared. Now let's go to the other reference frame. In the other reference frame, the event 1, left door closes. Let's also call its position x is equal to 0, x prime is equal to 0, t prime is equal to 0. We are just choosing our origin in the other reference frame, the origin of the coordinates and the origin of time. And then event 2. Now left door opens. Event 2. Right door closes. Well, it happens at time, non-zero time, at some later time. We are looking for what is that t prime. But the length of the garage is 4 meters. But the garage has moved. And it has moved, the end of the garage is now not at 4 meters, but at 4 meters minus, it's moving with a speed 0.6 c at the time t prime. So now this is the new position of the end of the garage.
By the time other door tries to open, it also moves, right?
Yes. Both of them move. So now what do we have? Well, delta x squared minus c times delta t squared in the initial reference frame is 5 meters squared. And this should be equal to, in that reference frame, in the other one, it should be 4 meter minus 0.6 c t prime squared minus t prime squared.
We can solve this, right?
Yeah. And from here you can determine t prime. If you want to use invariant intervals.
T prime squared, ct prime squared.
Oh, it's also ct prime squared. You're right. An alternative would be just to use the Lorentz transformations. You will be just translating delta x is equal to 5 meters and delta t is equal to 0. We are interested in delta t prime, and delta t prime would be just gamma delta t plus v over c squared delta x. And here v would be
0.60.
plus or minus.
It depends, but I would pick plus.
I would pick minus. You see, just how do you interpret this thing? Delta x is the distance measured in the other reference frame, in the reference frame of the garage. Delta t is the time measured in the other reference frame, in the reference frame of the garage. V is this velocity of the other reference frame, that is the reference frame of the garage. The garage is moving with a speed minus 0.6 c. Yeah, this would be easier. But both of them should give the same answer. Other questions? Somebody else?
The first question, I didn't understand.
What is the first question? Well, just assume that I don't remember any of the questions.
A spaceship goes towards moon, and I don't understand if it goes towards moon in an angle or it's not an angle. It's directly perpendicular.
Well, if it's not given, it probably goes straight.
Okay, so should we assume that the relativistic evolution, or we didn't?
Well, you see, relativistic length contraction or aberration or whatever is not an option. Everything has to satisfy the equations that we call relativistic. Everything. It is just under certain circumstances, you can just assume gamma to be 1 because it is very close to 1. And v over c you can just assume to be 0 because it will be very close to 0. So whether you should use the relativistic equations or the non-relativistic equations, you don't really have an option. The correct laws are the relativistic laws. Unless you have a justification to claim that they will be approximately equal to the non-relativistic expressions, you have to use the relativistic ones.
But the problem, my problem with this question was the direct movement towards moon will cause a contraction in its depth. Will it cause a size change in?
Read me the question. And the answer is? The width changes?
The angle of the approaching vehicle is changing.
Well, for this question, does it matter?
It changes, but you can't see it, I guess, because it's the depth change of the moon does not change the projection, I guess.
What you will see will not change if you are moving straight towards the moon. If you are passing by the moon, what you see will change. You see, if you are going straight to the moon, like this, what you will see is this one. It is just getting larger and larger as you are approaching. If this is the moon and you are just passing by, what you will see when you look out the window is that you will just see this one.
It's like the Neon's perspective of the Earth.
More or less.
On the ground.
Yeah, the question what was in my mind is similar to, I guess, my friends, because as we approach the length contracts, I mean, the moon gets thinner, but the picture should be like the same, but the curve gets the angle gets bigger. The radius of the moon looks like getting bigger. It's like getting flatter and flatter. The sides and the angles. I mean, what does that do to the image? I mean, that was a question. I mean, the Earth's surface starts to look like flat, and does it change the way we see? Because the light reflecting from that moon is the same for us.
You see, if you are in this direction, going straight to the Earth, the shape will not change. It will be just a circle. The radius will be exactly the same as the radius observed by somebody who is just standing at your position.
But his aspect is not the same.
His?
His aspect may not be the same.
His?
His aspect, the view. Because in this angle, for example, I cannot see the above, but if I go to the
Well, you see, in all these questions, what is usually implied is that you take away the effects of the. You see, when you say when we are talking about the length, we say that there is length contraction, but the length we see will not be that contracted length, unless we are just midway and looking straight. Because if the object is somewhere over here and moving with a very large speed, the light that reaches us didn't leave the endpoints at the same time. So what we will actually see will be much more complicated. But when we are discussing, what we do is we just assume that we just take away, we correct for these corrections. So what we will actually see with our eyes will be different than what the actual length or what the actual shape will be. Because at different parts, the light will come at different times. Now, for this circular shape, I don't think it will make any difference. Because if you are going straight through the center, well, the size will be determined by the rim. So the rim, the light leaves the rim at the same time, and they arrive at your eyes at the same time. If you are going straight to the center.
Can we convert this problem into general relativity?
No. Because I don't want to.
What you said just confused me, because when we travel through the center, the spaceship is going with the velocity of c, and
The spaceship?
and it will take the photon which transfers the information to the observer's eyes. Shouldn't he take it a long time from yani orada durarak bakan bir gözlemci var. Spaceship onun yanından c hızıyla gittiği zaman aydaki fotonun görüntüsünü aslında diğerinden daha hızlı bir şekilde almış olmayacak.
Well, you see, the speed of the photon that the observer sees will still be c. And it will only see the photons that are at that point. So whether you are stationary or moving, you only see the photons that are at that point.
Peki aynı zaman dediğimizde yani aslında t eşittir 0 dediğimiz anda ya da t eşittir 0.1 dediğimiz zamanda spaceship aslında belli bir mesafeye gitmiş olup aslında farklı bir yerdeki fotonu görmüş olacak.
But there will be one difference though. You see, at this point there is an observer at rest and there is the ship. So in this reference frame, the reference frame in which the moon is at rest, this will be the angle. This is the angle that you will see. The observer at rest will see. in the reference frame at that point, in the reference frame of the ship, it's the same size moon. This will be the angle. The angle will be larger. So you see, in that reference frame, there's a smaller angle. In this reference frame, the reference frame of the ship, the angle will be larger. The moon is moving now. But still, although the angle will be larger, if he calculates the radius, he should see the same radius. He will say that the angle is larger not because the radius is larger. The angle is larger because this distance is smaller. So when he takes all that changes into account, he will conclude that the radius of the disk that he sees will be exactly the same as the radius of the disk that this observer at rest sees.
John, you said where does he travel does not matter for this question about.
So in this question, well, okay, you see, depends on what you are looking at. If you are traveling like this, it does matter. If you are moving like this, it does matter.
But not exactly.
At the center, it doesn't matter. Because the rim of the disk that you see, they are formed by points at equidistant points.
I think it looks flat surface. I mean, it means there is a change in shape.
But, well, you see, when you look at the moon, does the moon look curved to you?
Not really, but
It's flat, because your eyes cannot really distinguish it. Of course, if you go and make more precise measurement, you will be able to determine the shape. I mean, even if you are going straight to the center, you can determine that this radius is shrinked. You can still determine it. But with your eyes are not so precise. Other questions? Somebody else? Yes.
In last lecture, you explained banding of light, and when we look out sky, there is no incompleteness in the sky, but we see incorrect with banding of light.
No. Why?
There is incompleteness, what we couldn't see because of a planet.
How large will that be?
How it's small.
Okay, let me just show you some images. Now, this is an example of a gravitational lensing. So actually, this is at least one galaxy which is behind the central galaxy. So why do we see such a circle?
Light bending because of this mass.
So this is the central galaxy. Some light will bend like this. Some other light will bend like this. So if you are observing from here, you will see some light coming from that direction and some other light coming from this direction.
I want to say that these lines with incompleteness in the back of the
So you see, let's see. So you are saying that here there should be some gap. How do you see that?
we see
I look straight. But if I look straight, I cannot see behind it.
we see wrong with this bending.
Yes? That's the idea of these shapes. I mean, the galaxy at the back doesn't have this ring-like shape. It's just the lens is distorting the image. But there won't be any gaps. In whichever direction you look, you will see something. Well, if we could look behind this thing, well, then we might have some problem. But we cannot look behind it. The lens is just blocking our way. But even here, there will be some light moving towards the galaxy, right? So there will be light moving in that direction, and it appears as some bright spot over here. There is light rays moving in this direction, which appears as some bright spots over here. There will be rays over here moving in that direction, and they will just come straight to us. Even if there was no central object over here, we could see the galaxy behind. If we could somehow find a way to remove this image without removing these actual gravitational effects, we would see the galaxy behind it. There's no gap. Are you sure that that is not a nebula?
I'm not 100% sure.
Neither am I. It doesn't make any difference in our arguments. If it's massive enough, it will bend light strongly enough to create such a ring-like shape. But nebulas, I don't think they are big enough. I don't think they are dense enough. But basically, the arguments doesn't assume anything about the structure of this lensing object, except that it should be very massive. Yes.
One of the questions in the assignment says that asks us if a collision happening in one reference frame and if it's elastic, can it be observed as inelastic in another reference frame or vice versa? I thought that it's an inelastic collision. If I put a heat or sound or something else sensor there and sense the heat that comes out from that collision, then it must be so in every other reference frame. So it cannot be elastic in any other reference frame. How true is that?
Well, so the question is, if we have a collision which is elastic in one reference frame, can it be inelastic in a different reference frame?
Or vice versa?
I would say no.
Why?
Why? Let's see. What does it mean to be elastic and inelastic? Energy is conserved and momentum is conserved. If in one reference frame energy and momentum are conserved, then in every reference frame they will be conserved. You see, momentum conservation, we started by assuming that momentum should be conserved in every reference frame. The way we define it, make sure that momentum, if it is conserved in one reference frame, so it will be conserved in every reference frame. I mean, we didn't discuss it in detail, but energy also has exactly the same property. In fact, you see, just like C delta T and delta X, you see, we can always think of them as a single entity. This is what we call a 4 vector. And why C delta T? Well, delta X is gamma delta X plus V delta T, and C delta T, now this is prime, is gamma times a C delta T, sorry, here let me also put C delta T, V over C, plus V over C delta X. They have the same units. If you look at the transformation laws, they are identical. How you go from one to the other one. And similarly, E over C and P, they are a 4 vector. They are basically the same quantities. If you go from one reference frame to the other one, one is converted into the other one. But if this 4 vector is conserved in one reference frame, it means it should be conserved in every reference frame. Well, you see, the conservation we have is this one. E1 over CP1 plus E2 over CP2. This should be equal to E3 over CP3 plus E4 over CP4. If this is satisfied in one reference frame, it is satisfied in every reference frame. You see, basically the conservation of energy and momentum. You see, when we were discussing space and time, we said that, okay, time changes, space changes from observer to observer. But we said that events, which is essentially these things, exist whether we choose an observer or not. Their existence or their equalities, their relationships to each other are independent of whether we choose an observer or not. The events exist. And we define their separation, 4-dimensional separation, etc. Now, this equality, this is what we call the energy momentum 4 vector. The energy momentum 4 vector conservation is the same in every reference frame. Or let me rephrase it. Energy momentum conservation exists. What is the energy of a particle? Well, it will depend on the reference frame. What is the momentum? Again, it will depend on the reference frame. But the conservation of energy momentum is something that is independent of reference frames. Because what is seen as energy for one object will be the momentum of the particles in the other reference frame.
Just wondering, my way of thought, can we say, is that correct? The experiment.
Well, you see, what I am not so sure is, if you remember our discussions about the garage problem, the resolution of, we had these sensors at the beginning of the garage, at the end of the garage, and there was one at the top. And one observer said that, okay, these sensors go on at the same time, and since this is right at the center, it will just light up for one observer. For the other observer, these two objects, these two sensors didn't go at the same, they were not simultaneous. Since they were no longer simultaneous, still this beamed up when both of them reached this point. So that was the way out. In your example, I'm not so sure whether there will be such an effect or not for the time being. So maybe it's heat in one reference frame, but it will be something else in a different reference frame. That is what I'm not so sure. Okay, blackbody radiation. What do you remember about the blackbody radiation? What are your questions? Any questions on the blackbody radiation?
I don't exactly understand how the neutralized catastrophe
Well, you see, the problem is this. Okay, so first, if you remember, we had defined what a blackbody is. A blackbody is essentially an object that absorbs all the light incident on it. This is how we define the blackbody, and all black bodies should be universal in the sense that they should, this is a statement about what it does to the light falling onto it. But black bodies also emit radiation. And then the question was, what is the spectrum of the radiation it emits? And all the spectrum emitted by all the black bodies has to be universal. They have to emit exactly the same spectrum. In fact, every object, if you just calculate how much it emits at a given wavelength at a given temperature, over how much of the light it absorbs at the same wavelength at the same temperature, this ratio should be the same for every material. And for the black body, we just set this to 1 So when we are calculating the emitted spectrum by the black body, we are actually calculating this ratio for every material, not just black body. And then we said that, okay, it is emitting radiation. So since it should be the same, this emission spectrum should be the same, whatever black body you have, we can just construct one black body. We just take this hole. You see, the black body is not the cavity. The black body is not this whole thing. The black body is this hole over there. That is what we call black body. Then the next question, why does it emit radiation? You say, how do we know that it is a black body? Well, you can just make sure that the walls are not good reflectors. So if there is light entering, well, it will be reflecting a couple of times, but eventually it will be absorbed. So the probability of this light again leaving this hole will be negligible. You can just make this hole smaller and smaller so none of it leaves. So this will be a perfect model for a black body. Well, why does it emit? Well, the walls, having some temperature, they are made up of charged objects which are constantly vibrating. So they are essentially emitting radiation and absorbing it. So inside, the cavity is filled with radiation. It is not the light that went through the hole. That radiation is created by the walls itself. Well, all that radiation, they are moving in arbitrary directions, in every direction. Some of it will escape. So if we have such a hole to a cavity, well, that hole will emit radiation, and the emitted radiation will be determined by the radiation inside the cavity. But since the emission spectrum of the black body is independent of how you create that black body, in this particular example, we created this black body by this cavity. Well, if we know how much this cavity emits through this hole, then we know the emission spectrum of the black body. Then we kind of converted our question. We started by asking, what is the emission spectrum of the black body? Now the question is this one. What is the spectrum of radiation inside the cavity? If we can determine it, then we can determine how much of it escapes through this hole. So what do we do? Well, I mean, you will be studying thermodynamic statistics in third year. So I will just mention some of the expressions. So the idea is you basically count, first you count in how many different ways this electromagnetic radiation in the cavity can vibrate within a given frequency range. So if you specify such a frequency range, just like the modes on a string, oscillating modes on the string, the electromagnetic radiation in the cavity will have various modes, and the number of modes within this cavity, within this frequency range, will be given by 8 pi nu squared d nu over c cubed times v. Well, d cubed k is the wave vector. You integrate over all possible wave vectors and all possible positions. That's how I remember this expression. So this is the number of modes, number of different ways that the electromagnetic radiation inside can oscillate. Then the next question is what the statistical mechanics tells us. It is before Planck time. We know that we had the equipartition theorem. Which states that for every degree of freedom, the average energy is kT over 2. Kb is just some constant. It's called the Boltzmann constant multiplied by the temperature divided by 2. Well, we have the number of modes per volume in the frequency range nu and nu plus d nu is 8 pi nu squared d nu over c cubed. This is the number of modes. Well, how many degrees of freedom does each one of the modes have? Well, when you want to determine the degrees of freedom, you just write down the energy. The energy of the electromagnetic radiation is some constant times the electric field squared minus some other constant times the magnetic field squared. No, plus. This is the energy. What is meant by the degree of freedom over there is just the number of squared terms in the energy. There's 1, there's 2. So electromagnetic radiation, each mode has actually 2 degrees of freedom. That one. How many such terms do you have in your expression? That's essentially what we mean by the degree of freedom. So there are different ways you can interpret this degree of freedom. The mathematical proof relies on the fact that how many square terms you have. A more physically intuitive picture will be, let's say the electromagnetic wave is moving in this direction. The electric field, let's say, is pointing upward at a given point. It can point upward, or it can be horizontal, or it can be in any direction. But any one of these orientations can be written as 1 or 2 different orientations, 2 independent orientations. So that's a different way of counting that number of modes. For electromagnetic waves, we have 2 degrees of freedom because of this, the possible different orientations of the electromagnetic radiation. Well, let's see. So we have this many modes. Yes?
So in total, if we don't know where the electromagnetic wave moves, can we say electromagnetic wave has 3 degrees of freedom?
No. You know that. You might not know which way it is going. But whichever direction it is moving, it has to be oscillating in the perpendicular direction. That you already know. The electric, even if you don't know the direction of propagation, given the direction of propagation, the electric field can only point in 2 independent directions. You see, in these number of modes, they are moving in different directions in the cavity. Some of them will be moving like this, some of them moving up and down, some of them will be at various angles. But I know that this is the total number, and for each one of them, I have 2 degrees of freedom, and I have this many modes. For each mode, I have 2 degrees of freedom, and the average energy of every degree of freedom should be kT over 2 by the equipartition theorem of classical physics. So this is the, let's say, du, the energy per frequency. If you would plot du by d nu as a function of nu, this is what you would get. And the larger the frequency, the more energy you have. But this is not what we observe. In fact, what we observe is this one. At a given temperature, this is what we see. Let's assume that the visible range is somewhere over here. Let's just say that this corresponds to the non-visible frequencies. This object will not shine. If you heat it further, what happens is this peak now moves to higher frequencies. You see, now it started emitting radiation. But most of the radiation it emits is at lower frequencies. So that's why it starts glowing red. If you heat it further, the peak will move even further to higher frequencies. This is what you will see at an even higher temperature. Well, now you see almost all the frequencies are emitted with equal amounts, more or less. So this object now glows white. Yes?
Will it be something like a normal distribution? Or?
That's not a normal distribution. We will write down the shape.
And what is the reason that why the peak, the amplitude of the peak decreases as the frequency increases?
But, I mean, the amplitude, well, in this plot, the amplitude doesn't increase at all.
Yes, I know, but in the book, the plots were like this.
Well, it depends on your normalization. And when you know the actual expression, the value at the peak doesn't really decrease. Mm-hmm. Well, you see, what we had said over here, let me emphasize it a bit further. For every material, its emissivity at a given wavelength, at a given temperature, and its absorption rate at a given frequency and at the same temperature, this is a universal function of lambda and t, which has a couple of consequences. One of them is if you just set A is equal to 1, like in the black body has A is equal to 1. So when you calculate the emissivity of the black body, the spectrum that it radiates, its radiation spectrum, then you will be obtaining this one. And so what this is, what you obtain is this ratio for every object. Second consequence is that since this is universal, I mean, you might come up with different black bodies, different ways of obtaining the black body. Well, physically, not a whole, but the darkest object we have absorbs, I think, 99.5% of all the light incident on it. That is the darkest we have. That is a black body. You can study its emission spectrum. This hole over here is the black body. You can study its own emission spectrum. Since this ratio is universal, the emission spectrum should be independent of how you create the black body. You see, here we have one way of creating a black body. The black body is not the cavity. The black body is the hole over here. And when you calculate the emissivity of this hole, what you obtain will be the emissivity of every black body, independent of how you create it. Whether you put a cavity on the back, or whether you create a very dark object, or whether you look at the sun. The sun is not a perfect black body, but it's a good approximation to a black body. So although the sun, as you said, doesn't have this cavity, well, my black body is this one, not the cavity. And all the emission properties of every black body should be identical, independent of how you create the black body.
Can you define the universality of that ratio?
Well, you see, the idea is this one. You just take two reservoirs that were at the same temperature, and then you, let's say, put another object at the same temperature. Both of them will be constantly emitting and absorbing radiation. The idea is if any one of them absorbs more than it emits, so the net effect will be it will acquire more energy. It will heat up. But thermodynamics just forbids the transfer of heat between two reservoirs of the same temperature. Since these are two different reservoirs at the same temperature, there shouldn't be any net heat flow. As much as this absorbs, it should emit. And as much as this absorbs, it should also emit. So that basically tells me that whether you are looking at object 1 or object 2, the ratio of how much it emits to how much it absorbs should be the same.
So the universality means this.
Yes.
So the ratio is always equal to 1.
No, the ratio is not equal to 1. You see, this ratio need not be 1. Okay, where was it? Yeah. This ratio need not be 1. But if you have an object that is absorbing more, it should also be emitting more. For a black body, this is 1. It just absorbs everything. But it should be emitting the most. If you have a shiny object, a mirror, this ratio is very close to 0. So this object should also be very close to 0. It doesn't emit.
So it is constant for a specific object.
This is constant. This is the same for every object. This is the same for a mirror. This is the same for the black body. This is the same for the sun. This is the same for your T-shirt.
But didn't you say it is
No. What I'm saying is each one of these factors will be different. For a black body, A is 1. For a mirror, A is very close to 0. For your T-shirt, this A is again close to 1. Your T-shirt is dark. But that means the emissivity should scale accordingly. If A is large for an object, E should be large for the same object, so that the ratio should be the same, independent of which object you have.
So it's constant for every object. The ratio is constant.
The ratio is the same for every object.
What constant is this?
That's what we are calculating. We are looking at the case when A is equal to 1. When A is equal to 1, so we will be calculating the emissivity, how much it radiates. So that will give me this ratio. So, okay, back to these curves. So this is the spectrum we observe. This is how it changes with temperature. The peak just basically shifts. We are initially this is the infrared. Then the peak approaches the red end of the visible spectrum. Then from the red end, it enters the visible spectrum. Then it goes ultraviolet, the X-rays, etc. But this is what is predicted by the Rayleigh-Jeans approximation that we used before. Something is wrong. We have to correct it. So if you were studying this problem, what would you do? Well, they just start together and this just leaves. So if you want to explain these curves, what would you do? Yeah, apply a fit. That's probably what Planck did. And what he came up with was, you see, Rayleigh-Jeans approximation is this one. Kt times 8 pi nu squared d nu over c cubed. Planck fit is just du is equal to 8 pi nu squared h nu divided by e to power h nu over kbt minus 1 times d nu. Well, he already knew about the Planck's constant. Now this is the Boltzmann constant. Now he had to, in his fit, he had to introduce one more constant. This is the fit parameter. H is called the Planck's constant. Well, I mean, you can test how it looks like at small frequencies. Let's say at small frequencies. E to power h nu over kt is approximately 1 plus h nu over kt. It's just a Taylor expansion of the exponential. So du now becomes approximately 8 pi nu squared h nu divided by 1 plus h nu over kt minus 1 d nu. The 1 and 1s, they cancel. H nu's, they cancel. So we end up 8 pi nu squared d nu over c cubed. Sorry, here I forgot c cubed. Times kt, which is nothing but our previous expression. So at least he knows that it should work at small frequencies, but it turns out that it works at larger frequencies also. So the next question is, okay, so he made a fit which explains the observations quite nicely. But what does this mean? So what does this function tell us? Okay, we will continue in the next hour. The first thing is, I said that, okay, it explains the observations nicely, but let's first look at, does it explain this shift? That the peak just moves with frequency? With temperature, sorry. So we will continue after 10 minutes.